Thank you, Anupam. Thank you for the invitation. It's a pleasure to come back. I was here 2 years ago. We had a long program on large deviations. And I knew that you have amazing Blackboard, so I thought I'll give a Blackboard talk. So the title is Dynamical Phase Transition in Markov processes. So the goal of the talk will be to explain, starting actually from what you know about phase transition, equilibrium phase transition, and explaining what a non-equilibrium or a dynamical phase transition is, and then presenting a very simple model where you can see such a dynamical phase transition. So this is work I've done recently with a student in Neurophysics Letters in 2016. So I'm not going to put all the details, so if you want the details of this, then you can look at the paper, and then there's a more recent paper with all the calculation in Physical Review E in 2018. Okay. If you have any questions, stop me along the way. I don't need to go through all the calculations. I'll just give a broad idea of the results and what it means in terms of processes and physics. So I'll start with equilibrium phase transition. Equilibrium. So the way we picture a phase transition, I think you know, is that as you vary a temperature, something sudden is happening. So if I have some control parameter, which we can picture as being the temperature, it could be the pressure, it could be, so for equilibrium situation, you have many control parameter, and then you're observing something like some order parameter. So it could be the magnetization of a spin model, or it could be the vapor density in a liquid fluid mixture. And so what you see is that for low temperature, maybe you see some value, and then after some temperature, you see some other value. So here I'm picturing a kind of magnetization phase transition, and the way I picture this, it looks like a continuous phase transition, which will be a second order phase transition. So you see something happening at some Tc, which is a critical temperature. So that's the way we see physically a phase transition happening. And as I mentioned there, this would be a continuous phase transition, but I could have also a kind of discontinuous phase transition where I have really at some Tc something even more violent happening, so I have a discontinuity in the observed value of the other parameter. So that's how we actually measure or see physically a phase transition, but that's not the way we mathematically study a phase transition. So what we study is more, we look at thermodynamic potential, and then we pinpoint a phase transition in terms of singularities of some thermodynamic potential. So what you would do, for instance, in the case of the magnetization phase transition, for instance, the Ising model, is that you'd calculate the partition function, you'll calculate the free energy, and then what you see is some kind of singularity in the free energy potential. So this is now a thermodynamic potential, and then for a second order phase transition, there's a singularity, which is a second order singularity at Tc. So the first derivative will be continuous, but the second derivative will be discontinuous. That will be a second order phase transition. If you did the same calculation for a first order phase transition, what you'd see generically is that now you really have some kind of corner at Tc. So if you calculate the first derivative of the free energy, it jumps. So mathematically, this is how you actually characterize phase transitions. And then it was a long-standing problem in equilibrium statistical mechanics to understand how singularities can appear in thermodynamic potential. So it was known that for finite systems, thermodynamic potentials are actually analytics. They don't have singularities, and so these singularities appear in the thermodynamic limit. And then this is now well understood, and actually something we teach at the undergraduate level with some specific models. So this is a general picture. And there's a third level actually of understanding of this, which is the microscopic and macroscopic appearance of phases. So here you'd say you have some kind of phase one, and then you have a phase two. So if you look now at the spin configurations, you'll see that those having zero magnetization are kind of disordered at high temperature, and at low temperature, they order to actually create a spontaneous magnetization. So I'm not drawing this, but if you're able to actually see the configuration, the microscopic configurations, you'll see differences in the way that these configurations appear, and these corresponds to the appearance of different phases. Okay, and then you can see this also at the two levels. So behind the emergence of a phase transition at the macroscopic level, of course, something is happening at the microscopic level. We're not seeing this, but you have different phases. And I guess it makes more sense if you think about the liquid-vapor transition, then it's clear that at the microscopic level, you have different phases. They're not behaving the same way. A gas, microscopically, you would have a gas or a liquid, so they are physically quite different. But the point of a phase transition is that you have this sudden appearance of different phases or sudden crossover between phases. And that's actually shown with the appearance of singularities. So it's not obvious actually that the phase transition physically like this would lead to singularities in the thermodynamic potential. And this is also a problem of statistical mechanics to explain why the singularities will have to be in correspondence with the phase transitions. But this is really also established. Okay, so the critical points here, so these are, the ideas here is that you have these singularities and an equilibrium transition at that point. So an equilibrium phase transition is a transition in the equilibrium state. Okay, so we're not talking about fluctuations at all. You just have an equilibrium state which, from the point of view of statistical mechanics, corresponds to a typical state. As you vary some parameter, that typical state will change. And mathematically, we can call this a bifurcation. It's a catastrophe. You can classify actually phase transition according to bifurcations as studied in dynamical system theory. There are really bifurcations. Okay, so I think that's the picture you know. Now I want to explain what is a dynamical phase transition in relation to this. Dynamical So the first thing I should say is that the word dynamical phase transition is used in many different fields, in different contexts, and means different things for these different contexts. So for instance, in quantum mechanics, you have this problem of the Loschmidt echo, and they talk and they study dynamical phase transitions. I'm not going to talk about this. Also, in fractal analysis or multifractal analysis, they have also this concept of dynamical phase transitions, and it's not related to what I'll mention. What I'll be discussing here is really phase transitions in the fluctuations of Markov processes. And for us, physicists working on this, we take Markov processes as being models of non-equilibrium systems or even equilibrium systems. So many particles interacting together, but in a time-dependent way. And then our basic model for this is a Markov process. So the picture I have in mind is the following. So we have a certain Markov process that evolves in time. So this will be the state of the Markov process. It's a random process, so it evolves in time. So I can think, for instance, of a diffusion, a kind of Langevin equation, and it's just evolving in time up to some time capital T. And then I can repeat the experiment or the simulation, and I'll see different trajectories. So the process will have different random trajectories, and the probability of these trajectories will be encoded in the model that we actually study. Now, what we look at actually is not so much, we're not interested so much in the statistical properties of the Markov model, but what we look at instead is some kind of observable, and I'll define what I mean by this. So you're not observing the trajectories, but you're measuring something else along the trajectory, and that's your observable. And what we want to observe, what we want to reconstruct, is the kind of probability distribution of your observable. So the probability that your observable will take some values A, okay? So if I do a simulation or some measurements, I'll be measuring certain trajectories, and then most of the trajectories actually will give me some typical property of the observable. So I'll be sampling more or less like the important region of the histogram or the distribution. But if I measure long enough, or if I simulate with more sample, then I can see some very rare trajectories which will correspond to values of the observable far away from the typical value. So it will be an actual fluctuation of the observable. It will be something in the tail, okay? And these we called a large fluctuation or large deviations, and I'll come to this later on, okay? But the point is that the object of interest is really that observable. The probability of that observable will actually come from the underlying Markov model, but also the exact nature of that observable, and I'll come to this in a second. Okay, so now what is a phase transition? What is a dynamical phase transition in that context? A dynamical phase transition will be a phase transition in the fluctuations. Okay, what do I mean by this? I mean that the kind of picture we're expecting, and then this is the picture I want to explain, is that if you look at the PAT, what you see often is that you see different regions of fluctuations. So the kind of cartoon picture I'm gonna put here is that you have a certain region of fluctuations on this side. It looks maybe like Gaussian, and then you get something that's really not Gaussian, or that's very different from the other side of the distribution. Okay, and that value actually that sort of marks the crossover between the two regions of fluctuations will be a sort of crossover point, will be the phase transition point. So a dynamical phase transition is really a transition between two fluctuations regimes. It means that on this side, you're going to have some kind of mechanism for producing those fluctuations. And if you look on the other side of that point, the mechanisms responsible for those fluctuations will be very different from those ones. Okay? Another way to picture this is that if I look at the trajectories that give rise to these fluctuations, they will have a similar behavior. But if I look on this side, I'll see trajectories that look very much different from that other set. So then I can talk of different phases of trajectories, and that will be the microscopic picture explaining why you have that critical point separating two different regions of fluctuations. So a dynamical phase transition, in this case, a DPT, will be a transition in the fluctuations. Okay. So what's the other parameter here? It's not like I have a control parameter which I'm changing and the order parameter changes as I change the control parameter. Here, in a way, the order parameter is the observable. And what I see is a transition in the actual values or likelihood of the values of the observable. I don't have an extra control parameter on the side. Okay? What I'll present later on, we'll see that we have a kind of control parameter. And the control parameter will be conjugated to the value of the observable. So I can picture the dynamical phase transition in a way like an equilibrium phase transition, but with a different control parameter, with a kind of effective temperature, but I'll come back to this. Huh?
Why do you call it dynamical?
Because the observable, we call this a dynamical observable. It's integrated over time, over the time of the Markov process. Okay, so these are actually fluctuations that happen in time. If I looked up to observation time t, I see fluctuations. If I have a longer observation time t, I'll see a different histogram. Okay.
So,
Yes?
the underlying model in both the regimes is the same?
Again?
The underlying model for
the underlying model is the same. It's just that the different values of the observable will be created by different phases of the same Markov process. Okay? In a fluctuation sense. Okay, this will become clear when I show the model. Okay, so this has been studied actually in large deviation theory, but also in the theory of non-equilibrium system for quite some time. And if you go into this, it's quite interesting, many different models, and most of the models will have many particles in a long time. Okay, so you have a dual limit where you have to take a long observation time to see the phase transition, in the same way that to have an equilibrium phase transition, we need a thermodynamic limit, right? We need a limit somewhere. Here it could be time going to infinity, or if you have an n-particle system, then the number of particles actually goes to infinity as well. Okay? And these models are not so easy to present. And so I was working with this with the graduate student, and then we just happened to find a very simple system where you see such a phase transition, and this is what I want to present. And this is the subject of these two papers. And the model is really dead simple. The model essentially is Brownian motion, okay? It's drifted Brownian motion, and then I'll define the observable, and then we'll be able to actually calculate very simply the distribution and then see that kind of phase transition. So I'll be spending most of my time actually explaining the model, showing just an outline how we calculate the distribution, and explaining how we see the dynamical phase transition there. So the model is drifted Brownian motion. a very simple model that you can write in different ways. I can write x dot is mu plus some kind of white noise. So this will be the white noise. So I have a constant velocity plus some white noise. Okay? This is how we write this in physics. I can also write this actually as a solution because this is solvable. So this is the position from some starting position will be now the velocity times t plus the actual Brownian motion. Okay? Or in maths, you could write this as a stochastic differential equation, will be mu dt plus sigma, and then you have your increments of the Brownian motion. Okay? They're all like three notations for the same process. But it's the simplest process you can imagine, other than Brownian motion. What you see is that if I look at typical trajectories, if I simulate this, what I see is your velocity mu, and then you have kind of Brownian motions around this. Okay? There are trajectories that actually go down. They have some probability, but this is very unlikely. If you simulate your system very often, then you see that they more or less follow that velocity. Okay? Now, of course, for mu equals 0, you get normal Brownian motion. For mu equals 0 and sigma equals 1, this is Brownian motion. And so there's no net velocity. It's just fluctuating around 0 there. Okay, so that's the basic process I'll consider. The observable now is what we call the occupation. Yeah.
So, the equilibrium S condition will essentially need thermodynamic limit.
So here I'm not speaking about time at all, right? There's no time picture for equilibrium because equilibrium statistical mechanics is all based on stationary distribution.
Right, but we need thermodynamic limit for this singularity.
Yes.
But in dynamical expansion, we essentially need T and B.
Yes, we do. And then we'll see this in the calculation.
If in some system it happens at finite time, that kind of change in distribution.
Yes, but you won't create actual singularities. So this is what we'll see. It will come with the talk. As I present the model, I'll be discussing actually whether we need a time limit or not. Okay. Ask the question again, and then we'll make sure we cover this. Okay. The observable now that I'll consider is what we call the occupation time. It's 1 over t, the integral of time of the indicator function for the interval -1, 1. Okay, this looks a bit arbitrary. What I do is that I take a strip around 0, and I just calculate the fraction of time. So what I do is I have +1 -1, and I look for an observation time t. I take a trajectory and I calculate the fraction of time that is contained between -1 and 1. So that's the observable. That's a random variable. That's my fraction of time that that one path would actually stays in -1, 1. I could take any other interval around 0. I don't need to take a centered interval, but it just makes all the calculation easier. I'm looking for the simplest thing now. It could be 0, 1, but -1, 1 actually symmetrizes the problem in a good way. So this is the observable. The case where the occupation is from 0 to infinity has been studied a lot, actually, long time ago by Levy. And then you have this arc sine distribution for that occupation time. So this is just a kind of specialized case where you have your indicator function. So this is equal to 1 if your process is in that interval, and then it's 0 otherwise. So really, I'm just calculating this is the total time spent in -1, 1, and I divide by t. So this is really the fraction of time I'm spending in -1, 1. Okay. So that rho t is a random variable. It's got a distribution. It's got a distribution over 0, 1 because the possible values of rho t itself is 0, 1. Okay, so if rho t is equal to 0, it means that the trajectory hasn't spent time in the interval. If rho t is equal to 1, it means that the trajectory spends all the time in -1, 1. Okay. The trajectory looks a bit like this. If I can sketch a bit what the trajectory looks like. So you have 0, you have 1, And it looks a bit like this. For a certain integration time, this is the probability that rho t is equal to rho, and this will be the values for your fraction, occupation fraction. This is for a particular time. If you take an integration time that's slightly longer, you get something like this, and then slightly longer, so you take something like this. So as time goes to infinity, it sort of concentrates onto zero, and the reason why it concentrates to zero is because the motion, the drifted Brownian motion, escapes to infinity because of the drift. So it's very unlikely that the process will stay for any amount of time in the interval. The natural tendency of the process is to go away from the interval. So in the long time limit, rho t will go to zero in probability, and that's the law of large number. Okay? But we can be more precise. There's actually a very nice result, and this is the connection with large deviation theory. The probability that rho t is equal to rho is to dominant order a decaying exponential with a certain rate that we call the rate function, and it's a function that depends on rho only. Okay, so this is a very simple form that tells you that yes, it concentrates, the tail decays exponentially with the observation time, and the rate of decay depends on some function that we will try to calculate now. So this is the rate function. So I guess we could say that 2 years ago we spent 2 months here at ICTS studying rate functions and then finding methods or discussing methods to get the rate function.
How do you know that answer is going to be?
In this case, I know this is the case, but the calculation will actually validate this. So I'm just like jumping towards the end result, but
If I want to do it explicitly, then what's the way to do it?
I'm going to explain this. Okay? So now the goal is to calculate this rate function and then show that this rate function shows something bizarre, and that's the dynamical phase transition. What we're expecting is that the rate function itself will have singularities. Okay? And this plays the role of the free energy. Okay? And so you see there's a kind of long time limit. I forgot to mention this, but this result is valid when t goes to infinity. Okay, so that rate function is defined actually as a limit, so it's a limiting function.
The interval from minus infinity to 0 wouldn't it be simpler?
Again?
The calculation from minus infinity to 0 interval. It's simpler than minus 1 to plus.
Okay, so if I take the full half interval, I don't have any phase transition.
From minus infinity to 0.
I haven't done that one actually. It could be there. It's something we could try. Yeah. We could do this, we can discuss this after. It might be actually. Okay. Okay, so the goal now is to show you how you calculate that rate function and then discuss singularities will appear and then we'll discuss the physical meaning of this and then we'll see that indeed they correspond to dynamical phase transitions. Okay, so how do we calculate rate functions? Now I will condense in basically 2 minutes something that we spent 3 hours, if not more. So if you want the details, there's actually a video from ICTS of 3 hours, 3 lectures explaining how you get rate functions. And I'll summarize this just on this piece of the board. So this is for calculation of the rate function. So the way we calculate this, and I'll do this actually for a general observable. I'll just spell out the theory for something that has the form certain function of f for my process like this. Okay, so the particular case that we're considering is the case where my small f is that indicator function. So what we actually attempt to calculate is what we call the scale cumulant generating function. That's this quantity. And a certain function, it's a limiting function. Time goes to infinity, 1 over time, the log, the expectation of t, k, at. And this is done, we need to calculate this for real values of k. So k is a kind of conjugate parameter to my random variable at, that's my observable. This is the generating function of at. Log of a generating function is a cumulant function because I take the limit. This is the scaled cumulant generating function. So we try to calculate this. The goal is to calculate this. And then there's a nice theorem called the Garner-Ellis Theorem that says that if lambda k exists and is differentiable, then my AT has a large deviation principle, so it has a large deviation form. So the density really has the form that I'm anticipating. So that answers the first question. When do we know that we have that approximation on ansatz or scaling? If we have the condition of that theorem, then I know I have that scaling. Moreover, the rate function in that case is given by a Legendre transform of the scale cumulative generating function. Okay, so this is a nice result. The logic of that result is that instead of looking at the probability, look at the generating function. And so if you can extract the scaling of the generating function, then you get all the information about the scaling of the probability. And so this is, it's not so clear that this is a Legendre transform, but this is a Legendre transform. Okay, it's kind of generalization that's called the Legendre-Fenkel transform, but for our purpose, it's a Legendre transform. Okay, that's only half of the calculation because it says that if you're able to calculate lambda k, then you have the rate function, basically. Now, how do we calculate the lambda k? So this is the other half of the calculation, and this is also a nice result. For Markov processes, the lambda k is an eigenvalue. So this is a kind of Penon-Frobenino result. And I'm not going to prove this, but this is a nice result. The lambda k for Markov process is a dominant eigenvalue. It's the largest eigenvalue of some linear operator. And the linear operator, we call this the tilted generator, is the original generator of the process plus kf. And f is the f here. Okay, so for my process, actually, for the drifted Brownian motion, this is easy. This is mu dx plus sigma squared over 2 ddx squared. This is the generator of drifted Brownian motion plus k, the indicator function over the interval. Okay, and then we call this the tilted generator. This is a linear operator. And so the goal now in the calculation is to find the spectrum of that linear operator in the Schrödinger sense. Okay, this is a linear differential operator, second order differential operator. The problem is that it's not emission, but we'll take care of that. And I need to find the spectrum, but not the whole spectrum. I only need to get the dominant eigenvalue. And once I have this as a function of k, I can check the Garner-Ellis condition, and then I can get the rate function. So the problem I have to solve at the end, this is the spectral problem I want to solve, is the following. I have the operator acting on some function, which I'm going to call Rk. These are function of the space. And I want to extract from this the dominant eigenvalue. So I have lambda k. And this Rk is the eigenfunction related to that dominant eigenvalue lambda k. Okay. So again, I could have the whole spectrum. I'm going to have different eigenvalues, different eigenfunctions, but I only want to extract the dominant eigenvalue of this. Now, the problem, again, you see is that this is not a Schrödinger problem. Unless you mu equal to 0, then this is a kind of Schrödinger problem. But because you have this is not emission. So we have to take care of this. Okay. So just to anticipate, so I'll show you the solution in two cases. The normal Brownian motion, and then we'll see there's no singularities in the rate functions or the arch deviation functions, and then I'll do the case just to kill the punch. For drifted Brownian motion, we'll do the same calculation, and something weird is happening because of this term, and then that leads to the phase transition, and then we'll see again physically why we have that phase transition. Okay? Okay, so let's do the solution for normal Brownian motion, so 5 large deviations for normal Brownian motion, so that means I take mu equals 0, so I have no drift. In this case, the motion is just a scaled Brownian motion. The tilted generator in this case is the Laplacian, so the second order derivative, plus k minus 1, 1, x, that's the indicator function. Now, if you look at this, you squint a bit with your eyes, you recognize a Schrödinger equation. It's exactly the form of a Schrödinger equation, and I can transform this to a Schrödinger equation by putting some minus sign at the right place and some h bars if you want, minus some v of x. And then you'll see now this is a Schrödinger equation. Okay? It's a Schrödinger equation for what potential? So it's a Schrödinger equation for this potential. I have a 0 level here for the energies. This is my x, so I'm just plotting v of x here. The depth of the well is minus k, because you see I'm going to put a minus sign here. So it's just taking the 0 potential and putting a hole between minus 1 and 1. This is what the indicator function does. Okay, it just creates a potential hole, so it's a finite well. Okay, quite nice. But now because I've put some minus sign, the lowest energy here will be my minus lambda k. So the ground state of the Schrödinger equation is my lambda k. My dominant eigenvalue that I'm looking for is minus the ground state of the Schrödinger equation. Yes?
Why does that function create that value?
Because you see, the indicator function is equal to 1 if x is in the interval and 0 otherwise. Okay? So basically I have 0 everywhere, but because I'm putting the minus sign here, I have minus k, so I'm just digging that well there for all the values x between minus 1 and 1. Okay? So that's a square potential. It's like the simplest case you can imagine. And again, the ground state will be minus my lambda k. Okay, and the depth of the well is minus k. So now what you do is that you open the textbook in quantum mechanics, you find a solution for the ground state. It's actually not explicit. It involves a transcendental equation, but you can solve this numerically very simply. And here's what you get. I can plot now the lambda k, which is basically the plot of the ground state energy as a function of the well depth. Okay, so this is an exercise I'm sure many of you have done. So here's the solution. This is my k, and I get something like this. Okay? It's asymptotically linear because when the well becomes deep enough, the ground state actually follows the depth of the well, but it's not quite the depth of the well, it's more subtle than this, but this is a calculation you can do. Okay, so it's fairly easy. With this now it's differentiable, so I can Legendre transform this to get the rate function, and here's what I get. It's defined again for 0, 1. I have an asymptote here, and I have my rate function like this. So this is my IR rho as a function of rho. Okay, and this is the Legendre transform. And then you see the most probable value of my fraction, my occupation fraction is 0, because this is where the rate function is 0. The rate function is positive everywhere else, so the density actually decays exponentially fast for every fraction, occupation fraction, except the occupation fraction 0, where it concentrates. So I get the rate function out of this quantum calculation. And this is something very general. The large deviations of the Markov process often can be transferred into, it can always be done using an eigenvalue problem, and then in some very special cases like this one, you can map this to a quantum problem. Okay? Now, for our point of view now, what we notice is that there are no dynamical phase transition. There's no singularity of this. The ground state of the Hamiltonian is analytic as a function of the well depth, so there's no singularities. This is just a Legendre transform, so there's no DPT there. Okay, because lambda k is analytic for k greater than 0. And then I can ask actually, and this is really what I want to emphasize, is that I want to understand now this rate function, what it means in terms of fluctuation path. Okay, so again, most of the path will have the value, the fraction 0. Okay, why is this? It's because if I look now at the trajectories leading to the fluctuations, most of the trajectories, and now I'm going to put some color, this is the A phase. The A phase is actually the typical phase. Most trajectories will escape, so they have no occupation fraction in the interval. Okay, so this is xt, this is my t. But there are fluctuations, so there are trajectories that have some occupation fraction. And so for instance, I can ask, what do trajectories that have a very high occupation fraction look like? Okay, and then I can do this in simulation, but I can do this also in calculation. And what I see is that these trajectories actually look like this. They are entirely contained into the interval, and I can actually describe them in terms of a stochastic differential equation. We know how to do this. In fact, it comes from the eigenvector Rk. Once we know Rk, we can actually define an effective process that explains those trajectories. So this is something I'm skipping over, but this is something quite interesting. Okay, so effectively, when you see a large occupation fraction as a fluctuation, it's created by an effective process that is confined. Now in the middle, if I can use another color, yes?
Where did you assume large t?
So it's all in the fact that I'm looking at this asymptotic. This is the dominant character of the distribution. And so it means that the rate function is actually obtained as limit goes to infinity of 1 over t log of the probability. So the rate function is really a limit object, okay? In the same way that my lambda k is a limit object, okay? So in fact, this lambda k plays the role of a free energy, and that rate function plays the role of an entropy, a thermodynamic entropy. But here, instead of taking a large system limit, we take a long time limit. Okay, so what about the region C? Region C are trajectories actually that spend some time in the interval, but not always. So they'll be like out, in, out, and they stay inside with a certain fraction that's between 0 and 1. Okay, so you see I can really relate that rate function back to the trajectory, and that's my microscopic picture. Okay? Okay, I'll finish more or less now with the interesting bit, which is the solution when I have a drift. Okay, so the picture is, this is where I see interesting things happening. So 6.
Minus 1 to plus 1. I guess the form of the function would be the same, just scale.
It would scale differently, but I'm expecting the 0 to be the most probable still. Yes, but it might change. Yes. The motion is drifted, so it's not going to stay. Unless, of course, you take the upper half line, then it's typical there, and then you're not getting anything there. Okay, so LDs for the drifted Brownian motion. I'm going to take mu greater than 0, but you could do the calculation for negative drift. It doesn't really matter. It's symmetric. The problem is symmetric. So the motion now is mu t plus the Brownian motion. The tilted generator, again, is mu ddx plus sigma squared ddx squared plus that k and then the indicator function. Okay. Now the problem again is that I have a non-emission problem. Now I have the fully non-emission problem. What I can do is that I can symmetrize the problem, and I'm skipping all the details here. I can also map this to a quantum problem, and the quantum problem is very similar. In fact, it's just a shift of the original problem where I'm just shifting the well. Okay? But I'm going to put the picture. What I get is for the lambda k, and then I'll try to be really careful in the way that I draw this. I have this branch which is the original eigenvalue of my problem with mu equals 0. So this is my lambda k as a function of k, and that guy is lambda k for mu equals 0 minus mu squared over 2 sigma squared. So it means that this is minus mu squared 2 sigma squared. So I know I have this eigenvalue. Okay? So I'm skipping over the details of the full spectral calculation, but I know I have this eigenvalue. But this cannot be the full solution because it doesn't go to 0 at 0, and so if you look for other eigenvalues, you see that there's another eigenvalue. It's lambda equals 0. There are other eigenvalues, okay? But I'm only showing 2. I know I have this one, I know I have the other one, and so there's an eigenvalue crossing, and large deviation theory would tell me that the full lambda k is the maximum between the two eigenvalues. So the lambda k is this. This is the lambda k. And so you see now lambda k is not differentiable. It's not differentiable at some point kc. What does it mean for the rate function? I can take the Legendre transform, and what's going to happen now is that I have something really bizarre. I have a full line, and then I have something like this. And there's a point here, rho c. There's the slope here is kc. Yes. Okay. So this is actually continuous, but it also has a singularity. But the main point here is that you have a first order singularity. The derivative jumps there.
This one and then that flat.
I know, taking the flat here and this one. It's a maximum. Yeah. Okay. And this has the right property because I know that at 0, lambda k has to be 0. So this is actually another way to choose it. Okay. By simulation, now if you pay attention, I've said before that I could only calculate the rate function if lambda k is differentiable. So how do I know that this is the right function? I know also by simulation. It confirms that this is the right rate function. Okay, but now I have a first order phase transition. So now I have first order DPT. And it's very simple. It's really like a simple spectral calculation that comes again from the quantum spectral calculation.
So what's the quantum problem?
Again?
No, what's the quantum potential?
So the quantum potential here is you're just shifting from 0. This is your 0, this is mu squared to sigma squared, this is minus k, and this will be your minus lambda k. But this will correspond, this will give you only that branch. So the other branch, lambda equals 0, is not in the quantum problem. It comes because you have a non-emission operator. Maybe you've heard actually doing quantum mechanics that in a quantum system you cannot have crossing of eigenvalues. This is only true for emission problems. Here you have a genuine crossing of eigenvalues coming from the non-emission nature of the operator. Okay? And then again, that eigenvalue is not in the quantum problem. You have to actually plug it into the equation to see that indeed it's an eigenvalue and there's a corresponding eigenfunction which changes as a function of k, but the eigenvalue does not change as a function of k. It's constant at 0.
Where does mu enter in this phase diagram?
So it enters in the way that you're shifting. You see I'm shifting the quantum solution by mu squared, and so the kc actually depends on mu and sigma here.
And in the second one?
In the second plot, the kc would actually give me this, and here the slope of the lambda k gives me the rho c, so this depends also on mu and sigma. Okay, when mu is equal to 0, that rho c actually goes here, because I'm shifting the lambda k back to the quantum solution, so when mu goes to 0, the phase transition disappears. But there's a phase transition for any mu non-zero.
But is it known how it depends on mu?
No, I can find asymptotics, but there's no explicit solution because there's no explicit solution in closed form for the well problem.
So I think you need this finite integral from -1 to 1 because otherwise you will
Yes. Well, it's something that we could look actually. Okay, so I want to do the same picture here. I have A, and I have C there, and B, and I want to draw now what's happening in terms of trajectory. So again, I have a -1, 1. A is easy again. A is a typical behavior. We're not talking about fluctuations. So for A, these are the escaping trajectories. These are the natural trajectories of the motion. They go to infinity. They're transient. And so most of the trajectories actually behave like this. So this is why you have the typical behavior at 0. B is, again, if you look at high fraction value, that corresponds to trajectory that spent a very long time there. If you look at the effective process there, it does not depend on mu. This is amazing. So when the process actually behaves in a fluctuation way to have high occupancy, it's forgetting the mu. It's confined in the interval, and it does not depend on mu. It's exactly the same process as the other one. Okay, it makes sense because if you have a drift, you'll necessarily escape. So if you want to stay in, you cannot have a drift. What's interesting is the middle part. So if I look at now the C there, what are those trajectories? So there's a critical density actually at which things will escape. So this is, the phase transition is related at the end physically to a localisation-delocalisation phase transition. Okay, so these ones at C, what happens is that you stay for very long in the interval. So you behave in a confined way, and after some time, you escape. And the proportion of time that you stay inside is just depending on the mixture of the two phases you have here. So this is a bit like a liquid-gas mixture. This point, the trajectories here behave like A for some fraction of time, and then they behave like B for some other fraction of time. This is what it means. And then we can describe this again with that eigenvector that I erased before. Okay, so we have a clear physical picture of why we have the phase transition, and now the first order DPT is really a discontinuous phase transition between those two phases of trajectories. This is what's happening. Yes?
In last section, we always look at asymptotic in time.
Yes.
So what do you mean first half of the...
This is so that time actually scales like the observation time. So if you take a longer observation time, you'll see that it stays longer in the interval, but with the same fraction here that you have. Okay. Okay. So that's more or less what I want to say. Yes.
Different for trajectories beyond that critical point.
Okay, so beyond that critical point, what's happening here is that the system actually forgets the drift. So if I have now another color, yellow, white, if I look now here, D actually is just like the original problem. It stays out for some times, but then comes back. And it does not depend on mu. Okay, so it has no drift. So the region here is a coexistence region where the drift plays in terms of delocalization. So these are delocalized trajectories, and the other ones are localized regime. So this is localized here, and this is delocalized. And you have first order phase transition between the two, this continuous phase transition between the two. And then you can see this also in the eigenfunction. You have an eigenfunction which is confined, and then on the other side you have an eigenfunction which is totally deconfined. Yes?
In the case mu equal to 0, there were two kinds of trajectories. The ones that went like the yellow one.
Yes.
And there was a symmetric one that also.
Yes, yes.
But this,
No, not, oh yeah, symmetric, yes, yes.
that is broken.
It's broken, yes.
So if you actually go down, you actually come back up.
Yes, yeah, yeah.
So that contributes to what kind of trajectories?
It could be actually the white ones, actually. The white ones could go down, but then they'll go up eventually and go, so, but because they actually forget the mu, they'll behave just like Brownian motion. So that D region behaves just like Brownian motion, this one like Brownian motion. So it's only A will have the one-sided drift. And the C is because I start at 0, actually in the definition of the model, they first stay in the interval. It costs less to stay in the interval and then escape. And then it will escape necessarily on this side. So there are trajectories that go negative, but they are a very small probability. So they don't really contribute to the picture there. Other questions? Okay, maybe I'll just finish with one comment. When we finished the calculation, we were quite satisfied with this because it's a very simple model that has that phase transition. And then a friend of mine, Yarif Kafri, just mentioned, there's the same phase transition in pinning, depinning transitions in superconductors. And then I had a look at the paper, and the solution is exactly the same. Okay, it's with that potential well and the same eigenfunction, but it's a totally different context. It has nothing to do with Markov processes and dynamical fluctuations, but you see this localization, delocalization phase transition. And I thought I'll just draw the picture for the correspondence so you can see if you're familiar with this, what this corresponds to, but it's just like a formal mapping that just preserves that phase transition, which again is a localization, delocalization phase transition. So this is the conclusion. It's the mapping to something that was studied by Hatano plus Nelson. There are 3 papers to look at, 96, 97, 98. This is in PRB. And this is the picture. So you have a kind of superconductor cylinder like this. You have a current that goes through it, which means that you're going to have a magnetic field coming from the current like this. And then what you have also is another magnetic field that goes up like this. And then you're looking at the dynamics of the field lines generated by this B. And if you look at the field lines, because you have that current there, you can look at the field lines there, but the superconductors will have defects, and the defects will have the effect of localizing a field line. So you have something, I'm just going to draw, and then you have a defect in the superconductor that has the effect of pinning the feed line of the B field there, and then it can move like this because there's another B field there, so it's going to move around, and then it could hit another defect, and then it's going to be pinned, and like this. So you see that the mapping with this model is that the occupation region is basically the defect, it's the pinning of the motion along defects of the superconductor. So this will be the time axis for me, and this is the x-axis. Okay, so I have a kind of motion of a Brownian walker that's pinned by defects. It's moved up in time because of that field. It's pushed with a drift because of that field. And it's just encircling the superconductor. So the drift is actually induced by the current that has that field there. And what's happening in the localization-delocalization is that there's a kind of strength for the defects that will actually pin the field lines. So if the defects are strong enough, you don't see any rolling of the field lines. The field lines will be pinned by a critical strength, and that's the localization transition. And so that point of localization-delocalization in the simplest model of this is exactly of that kind. Okay, but you see that it has nothing to do with the Markov process as such, but it's just a formal modeling of the physical system. So it's quite interesting. If you're interested in this, have a look. The mapping is quite cute, and so it really goes beyond this. And amazingly, the interpretation was really the same too. So we included that in the second paper. We weren't aware of it in the first paper. Okay. So good. Thank you for your attention.
So like normally random this Brownian motion could map it to a polymer, right?
Yes.
So I mean then it looks like it's probably going to interpret as a polymer.
Yes.
Is it the same as this?
Yes, so I have other papers, I'm not mentioning this, but the absorption transition for polymers is of this kind too. So you have kind of on your surface, you have your polymer moving, and then it's pinned down by some local potential on the surface, And if you have enough pinning, enough strength of the pinning, you really keep the polymer down as opposed to having the free polymer floating above the surface. And people have looked at this, and you see also phase transition, but it could be first order or second order depending on the model that you look at and depending on the condition. I'm not fully aware of the details, but you have two kinds of phase transition in that case.
No, but shouldn't it be possible to map it exactly to a polymer?
Yeah, in the one-dimensional case, I think you could. Yeah. You would have a field that actually pushes the polymer up, so that will be like the drift, and then you have a potential to pin it down, and that will be the like looking at the fluctuations in the potential there.
It's called loops. That might be very, very fine.
Yes, yeah.
My question was, this could also go through for discrete state models, right?
You could see this.
You're not able to calculate, but you will do.
I guess like just in the bias random walk, you should be able to see this. Now, the point I forgot to mention is that the fact that the motion is on the real line and it's transient on the real line is really important. In the paper, we also asked, so we asked the question, if we confine the motion, do we have the phase transition? And the answer is no. If you put the diffusion on a ring or in a box or in a potential, you lose the phase transition. So the fact that the motion is transient and so non-recurrent on the real line, but the fact that it escapes to infinities, this is what I mean by transient, is really important. So if you confine the process, again, it becomes recurrent now, it becomes an ergodic process, and there's no phase transition. So in the paper, then we just take a confinement, and then we take the deconfinement limit, and you see how the phase transition appears.
By just looking at the trajectories, you cannot say whether it's first order or continuous transition, right?
Again, is the...
I mean, like, just from the trajectories, you cannot say whether it will be first order or second order.
No.
Because in the second order, you can have the same interpretation in terms of the trajectories.
Yes. Yeah.
Is there a way to modify this in a way that you get two critical points?
I guess you could have, I don't know if you have like two occupation region that would correspond to two pinnings in the superconducting case. Maybe you could have two phase transition. It could be. I haven't tried this, but there's yeah. In the confinement problem, what's interesting, you could have this because when you confine the process, what you have is that you have that potential. So I'm confined process, but I have that hole. So the phase transition is actually between a delocalized wave function, and then if the well is deep enough, it falls in the well. So if I have two competing well, I might have more than one phase transition. Okay. Interesting.
The other observable photos you see
With only the time limit, no. So again, in our field of large deviations, dynamical phase transition had been seen before, but for many particle models. So for instance, exclusion process on the real line, so on the lattice, the one-dimensional lattice, or 2D exclusion processes, or something like the East model. So they're more complicated process, and then they evolve at double limit, so number of particles going to infinity and integration time, and then the observable is different. So they look at the activity or at the current, and then you have dynamical phase transition at the level of those observables.
The second order you can see.
I guess, yeah, you could do that, yeah.
Then you can position.
But then it's a different, you look at the position itself, right? It's not an integrated observable.
They are also in the same trajectory as localized.
Yeah. Thank you.